Hello, Daniele.
Hey, hi, Simon.
Nice to see you.
Nice to
You have
see
a
you
wonderful
too.
background.
Yes.
Yeah.
I also made up a logo for the conference
Yeah.
myself.
Oh,
You saw?
wow.
You saw?
You make it yourself?
I should sell it. Okay,
Nice.
so you confirm you see myself and the slides and you hear okay, looks like.
Yeah.
So we already
Wonderful.
made it sound check. Okay, very good.
Yeah. Okay, wonderful.
Okay, so it's 9 a.m. I saw people connected and potentially also others will connect later on. So why don't we get started just on time? So welcome everybody. My name is Daniele BONACORSI. I'm spending some hours with you today on a machine learning workshop, which will be a sort of a beginner intermediate level discussion on machine learning topics that will go through some presentation and at the same time some possibility for you to check something on code and try things out. So it's a very intended to be a very interactive and dynamic kind of day. So I will be speaking a lot, but feel free also to interrupt me and speak somehow yourself in the middle as much as you want. Okay, so let's get into the game. So first of all, let me grab back the. Okay, so we need to start with some logistics first of all. Okay, so the plan for the day is the following. We have basically 4 slots with breaks in the middle, including the lunch. I will start with some basic introduction on machine learning concepts and the tools that we might need and use. It's everything far away from a theoretical kind of machine learning introduction. It's more the flavor of the applied machine learning that I'm trying to give you. And so we will be as pragmatical as possible. So no theorem, nothing heavy, just a discussion about the key topics. And then we get quickly into some labs. The labs are intended, as you will see, in a very dynamic way. So you decide what you want to do. There is slide material in which I will be explaining something to you, some of the approach, how you attack a problem, what to do, the code you write, comments in the slides about the code and things like this. And you can follow what you want. You can decide to just sit down, sip a coffee or a tea and follow the discussion, or actually go to the code yourself that is available to you and basically also use it at your convenience. So you can follow in real time and code in real time, or just follow and then exercise later. All the slides are available to you. They are already linked on the ISGC website. And all the code material, it's available and will be available to you, so you don't miss any single line of code. And it's not linked anywhere at the moment, but the link is in the next slides, and I will be putting in due time also on the chat window of this Zoom meeting, so that also latecomers that might not have that link will get it before we get into the code. Okay, so you decide basically how to follow the day. I'm here for you. You decide how to make use of these hours with me. So oops, the material indeed will appear here, okay? And also look at the bottom when you see something like time to code, it means that there is something on the repository of the code where you can play things, okay? Okay, so let's start with the definition of machine learning, or actually I would say the definitions of machine learning, because there is more than one. Let's start with some textual definition first of all. So as you might know, machine learning is difficult, is something that people know, but it's actually relatively difficult to define very strictly. So there are various definitions that came up over the years. So from the Oxford Dictionary of Statistics terms, it's the capacity of a computer to learn from experience, so to modify its processing on the basis of new information that it acquires. Actually, Arthur Samuel gave a very nice and common and famous definition. So machine learning as the field of study that gives computer the ability to learn without being explicitly programmed. We will come back to that. Another definition, very famous, from Tom Mitchell, it's more, let's say, pragmatic. So a machine learns from some experience with respect to some class of task and performance measure if the performance it gives at given tasks as measured by that performance measure improves with the experience. So it's a very nice way basically to define machine learning like that, because it's sort of an operational way of thinking about it. Okay, there is also another way to define machine learning, perhaps very useful, especially for a beginner, so a visual way. NVIDIA decided to sort of depict where machine learning stands in the scenario of artificial intelligence in this picture. As you can see in this picture, there are various ways. First of all, there is a time axis. it tells you very clearly that basically artificial intelligence was there decades ago, before machine learning came up, and machine learning was there before actually deep learning came up, which happened over the last 10 years or so. Additionally, in the plot, you see also that artificial intelligence somehow contains machine learning. So you can work on artificial intelligence without having anything to do with machine learning. Okay, so it's not really proper to talk about artificial intelligence too much if you are not really intending that specifically. Machine learning is a way to implement artificial intelligence, if you want to see it that way. And later on, deep learning was a sort of an additional specialization of machine learning techniques. Okay, so they are in the middle. And also it's very nice from the pictures that you sort of connect mentally to the kind of tasks that probably these areas were most famous for. So artificial intelligence to with machines that play games with humans, and you would like to beat the machines or the machines beat the human. Machine learning with the technique that actually with a lot of data can do some interesting tasks like flagging mails as spam is a very typical and let's say hello world kind of application in machine learning. And deep learning, of course, connects a lot with images and computer vision, for example. So indeed, before going on, let's clarify that the AI terminology is somehow a bit misleading in most of the practical discussions that we might have here. So most of AI research today, not all of it, of course, but most of it is not trying to recreate intelligence in any shape or form at all. So more than talking about artificial intelligence, in many cases, especially in the context we are working together on today, it's much better to think about automation of tasks, okay? So being able to automate the task execution in a way that basically you can also feed this stuff into some decision-making process. This is probably the best way. So we are trying to collect the data around how humans make decisions in a way that you can perform the same task that humans could do, but at a very large scale and a very small latency at the level that humans, of course, cannot afford to achieve. Like facial recognition, for example. For sure, you know something like thousands of faces. And if you ask a machine to recognize faces, probably is able to do it for million or billion of faces, and even much faster than you are in some sense, if it's taught to do so, okay? But that doesn't mean the machine is more intelligent than you. It's not artificial intelligence better than your human intelligence. It's only that at very specific tasks, the machine is able to do things at large scale, at a small latency, much larger scale and much smaller latency than you as a human are. This is basically the artificial intelligence we are talking about here. So a way to implement this kind of automation of task executions and prediction and then decision making is indeed using machine learning techniques. Actually, why do we talk about this stuff now and not decades ago? Because the pictorial view by NVIDIA told you that basically everything started in the 50s. Well, the 50s were basically 70 years ago. So why didn't it happen before? Why are we talking about deep neural networks today and not decades ago? Indeed, so long time ago. Well, there are various reasons. One of these is definitely the technology. We had a huge improvements in the computing capabilities thanks to hardware the design and development over the recent years, and this is definitely a changing factor. But actually it's more complicated than that. There are various aspects that are important. The first is the rise of big data. We will see that these basically are techniques that are used for data-driven modeling. So the more data you have, the more richness you can get from the data, well, the more fuel you have for your machine somehow. So it works better, actually cannot work without. The second aspect is indeed the technology. Probably we should thank all the gamers worldwide here because they were the first heavy utilizers of general purpose graphical processing units, or at least they pushed the move from GPUs to actually general purpose utilization for science and industry. Definitely this is a big game. A lot of machine learning has to do with linear algebra, so highly parallelizable operations, and GPUs are basically there for that. So the progress of the technology came only recently, and this is definitely a changing factor. A third aspect is the fact that if I need these computing resources, probably I would have needed since a few years ago to just buy them and to maintain and to have electrical power and to have UPS system to make sure that everything stayed always live and active okay, and without interruptions. I need to change the machines that get old, all these kind of things. You cannot afford, of course, at large scale to have a data centers for yourself. It simply doesn't scale. Okay, it doesn't work. You don't have the money, you cannot maintain it, etc. So another thing that came up to the game is basically the democratization of the access to massive computing resources thanks to cloud interfaces. Well, I use the democracy kind of word a bit with caution here, because of course it's democratic as long as you have the money to hire these machines on clouds, but actually you could not afford to build a data center in your garage anyway. So at least if you have a project, if you have some funding, you can in principle for a relatively limited amount of time, but have a data center that is comparable with large data centers. So the moving of these resources from needing to be on premise and being able to be hired, let's say, from clouds is definitely a game changer. So all these kind of things made the machine learning just jump to the roof, and especially also deep learning, and made it become one of the core transformative technologies that we have nowadays in all worldwide activities that are able basically to extract actionable insight from a very large and diverse set of big data. Okay. So if this is it, oops, the slide sort of froze. Okay, they got back, sorry. Okay, another definition to move then to what we need to talk is the one from François Chollet, which is the author of Keras, by the way, that we will be using. He said that the classical programming is based on using rules and data to produce answers. Actually, machine learning changed the paradigm in the sense that it uses data and answers to produce the rules, which it's strange if you think of it. But actually, if you think of supervised learning, as we will be discussing it's not so weird. So you don't need to have exact rules, but actually if the data can tell you which is a pattern that you might use to get to an answer, basically you can extract some rule and then basically you can have new answers there. So we will see basically how that works, because traditionally the approach is very simple. You need to study a problem, you write some rule like if then else cycles in programming, just make it as simple as possible. You need to evaluate if your program works, and if it works you launch it. If not, you analyze why it didn't work, you study back the problem and you write new rules. So basically this is the typical way of programming somehow a machine. The new way of programming the machine that actually is behind machine learning is that you don't write the rules. You get the data fed into a machine learning algorithm that you train. So you explain basically how to use this data to extract something out of this data. Then you evaluate the solution. If the solution basically is fine, you go to production. Otherwise, you analyze and you continue training, basically even with more data. You see where the game changer here is the data. Okay, so everything is based not on your ability to write the rules, but actually on your ability to collect meaningful, rich, expressive data to train your machine learning algorithms. And this is the game changer, right? So you understand why big data play a role here, because if you have lots of data, I mean big data in the term of the volume, you know that big data conceptually are defined with different V's like variety, velocity, veracity, but also volume. But it's not only big data in terms of large data volumes, it's also the richness of their diversity and things like this. Then basically this allows you to train better algorithms, and potentially this is what makes the machine learning approach successful. Okay, so said this, let's go into the different types of machine learning, because there are various ways to classify things, and definitely it's a wide area. So let's try to make some context in little boxes to be more precise and more concrete. So there is a very traditional, quite lightweight classification of machine learning in different types in terms of the way they learn. So which are the learning algorithms, which is the procedure, the protocols to learn. Okay, the three most populated categories, there are some in the middle, there is semi-supervised, self-supervised and whatever, but the main categories, let's not go into too many details here. It's supervised learning, unsupervised learning, and reinforcement learning. So the supervised learning is with the supervision. So the machine learns by your supervision. So somehow there is a way to teach the machine how to learn something from the data. It's not unassisted, it's actually assisted and supervised. Unsupervised is the opposite. You let the machine basically learn by itself from the data. Reinforcement learning is a completely different beast because basically you make the machine learn by feedback. Okay, these are basically the three classification, but actually you can do more than that. You can classify machine learning in broad categories by thinking about what we did, so the way they are trained, so the amount of type of supervisions, and this indeed allows you to have the categories that I told you, but you can also classify machine learning methods depending on if they are able to learn incrementally on the fly, for example, by being given more data, and this is the online learning versus the batch learning. Or you can actually decide to classify these based on the fact that they may be comparing new data points to no data points, or instead they try to use all the data points to detect some patterns in the training data to build a predictive model. So this is instant-based learning versus model-based learning. We will say something about these in a second. These criteria, of course, are not inclusive. They are simply taking in the complex phase space of the definitions, different aspects, and putting these on the table to distinguish. But actually, you can use them all together. For example, if you have a machine learning-based spam filter that is quite advanced, so it uses good machine learning techniques, it can learn on the fly using a deep neural network, for example, to distinguish non-spam and spam mails. This will be potentially, if it's get continuously trained and actually builds a model to do the forecasts, and you actually gave labels, so it's a supervised, it can be an online model-based supervised machine learning system. So you can fit, you see, in the different categories, any single model by assigning in which of the choices you are among the choices that I told you. So let's try to see a bit more what these different concepts and classification may look like with some examples. Do we have a chance? Because it becomes already complicated, but can we make it simpler than that? I'm afraid no. So this is probably the only way to classify machine learning problems and methods, because we need to do some selection and to decide what we want to do, what we want to discuss on, and so on. The alternative would be to get into every single machine learning algorithm, and there is quite a zoo, and definitely this is even close to impossible in an entire course on machine learning. So I presume it's really impossible to do it in one day. So you need to allow me some simplification and classification in major classes, okay? Okay, so supervised, unsupervised, and reinforcement learning. Let's try to understand a bit more what that means. Supervised learning, it's indeed machine learning that happens with supervision. So the examples that you are given, the so-called data entries or instances, okay, are being fed basically to you from the outside, okay? And these have characteristics that are called in jargon attributes that you may decide to use them or not in machine learning. So in this case, conceptually, the attributes of your data entries can be defined as features. If they are features, it's something that you use in machine learning, okay? The process by using the features of the training examples is called the training. So you train a model on your data set examples or instances based on the features that each of these examples have, okay? This is basically the jargon. But also this data includes the truth information in supervised learning. So you have the so-called labels. For example, in a spam detection problem, the system is checking if you select this is spam or this is not spam for every single mail. And so it learns by your supervision. You are giving the labels. And once you are just giving to the system a new mail, probably it has learned from your actions, which are the labels, if the new mail is more similar to something that would have flagged as spam or to something that actually you would have read as a good mail, okay? This is basically the supervision, and it's used a lot everywhere. So in image classification, in speech and text recognition, in the medical sector for diagnosis and beyond, fraud detection and things like this. Every time you have the way to supervise, in a way, you help the machine. So the model gets a bit better. It's not always the case, but when you can do it, supervision definitely helps. Supervised machine learning problems can be different, and we will discuss also in the lab the cases of this. It can be a classification or a regression case. In the classification case, you predict classes. So it can be a binary classification, so yes and no, 0, 1, to specific question like spam, not spam, for example, or multi-class. So just tag an animal out of an image. It's not only 2 animals you have, you might have 7 animals or 100, okay? Regression instead is different because you predict numerical values in a continuum range of values. So you can predict the price of a house or things like this. So numbers, specific numbers. Actually, it's more complicated than this. Some regression algorithms can be used for classification, but let's not go into that detail. So you see that classifying and doing regression are typical supervised tasks that we might approach. And we have also little labs later on today on these topics. In terms of supervised machine learning, just to give you a feeling of the most popular algorithms, the most commonly used algorithms are like linear regression, logistic regression. The first is very simple for regression. The second is actually for classification. Support vector machine, k-nearest neighbors, all the decision trees family, including random forest, of course, also neural network, at least those that can be considered supervised. Okay. What is unsupervised instead? Well, in unsupervised learnings, you don't have the labels. Okay, all the training data is unlabeled. So you are given the data, but you know anything about any single training example. Okay, you don't know what they are. You don't know the truth somehow. So the system needs to try to learn something without the teacher. Okay, it's self-teaching somehow. So suppose that you are collecting some data about blog readers, as per the example before, you can run an algorithm that is unsupervised, that is able to extract groups of similar visitors, okay? Maybe found out that 30% are females who comment on the posts of your blog on a given topic, read the blogs in the evenings, and things like this, okay? So these kind of algorithms don't even know which are the groups that are being formed. They just simply extract similarities from the data, okay? Unsupervised can help a lot in visualizing networks, in analysis of social networks, for example, or also for astronomy or things like this, to find some patterns in nature by exploring basically large volumes of data without actually being able to provide any possible supervision. So you can organize large computer cluster with unsupervised learning, for example, which are the machines that try to work together. So you may set up a data center that is more efficient. You can analyze social network. So which are the friends you message the most? Or given the connections that you have, which are some cohesive groups you would like to be part of, or which are the people you should actually know already, and these are those accounts, so suggest these kind of things. It's used a lot for market segmentation. So having a lot of databases, huge databases of customers information, you can try to automatically group customers into different segments in the market, so you can do some advertisement and offers that are more targeted. And definitely in science data analysis in general, clustering algorithms is a good example on a way that to provide some insight into possible logical grouping of things that actually would be otherwise completely disconnected. An example on supervised learning that came out in Nature some time ago was an analysis on skin cancer. It's unfortunately a cancer, but actually is a cancer that you can diagnose by looking from the external of a person. So it's really a visual kind of diagnosis that you can do, and actually dermatologists do. And a good unsupervised machine learning is able to detect across a lot of pictures of this disease which belong to most probably one category and which one instead belong to which other category. Then of course you need an expert to say which are the categories that are being built, because of course it cannot distinguish a melanoma from something else, the machine, but actually it groups these together because they look morphologically and visually similar. So this is a kind of an unsupervised approach. And it's very used also in visualization. It's a large customer of unsupervised learning algorithms. Basically, you have a lot of complex and completely unlabeled data, for example, and you can use these algorithms to have a two-dimensional or even a three-dimensional representation of the data to be plotted in groups and things like this. So this is really a nice application. In terms of unsupervised machine learning algorithms, there are various. There is a variety of these. There is definitely the clustering family that tries to detect the groups in the data like k-means, DBS-can, HCA, and blah, 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 many more. For visualization and dimensionality reduction, definitely there are some that are so used, like principal component analysis used here, despite being a dimensionality reduction tool used here as an unsupervised algorithm, or kernel PCA, LLE, the TSNE, etc., and so on. So there is a large set of algorithms also here that unfortunately we cannot discuss in all the details, but just for you to know that there are so many. The third family is reinforcement learning. Reinforcement learning is a completely different object, and you can see also very easily. There should be a video if I'm able to get it started. Here it is. It should be starting in a second. So basically this is a little game of a ball, a red ball, that is pushed towards a machine that has a camera in front of it and should be able to get when the machine is coming close and actually stop it, okay? Stop it from making the goal. And this is not so easy. Definitely, it takes some time. But if you see that if at the beginning the performances was awful, in intermediate steps, you see the machine at least trying to go towards the ball, despite definitely not being able to catch it yet, at least. But if you continue to do so with a large number of trials, you get some decent performance, and the machine is able to catch the ball basically all the times that the ball gets thrown to it. This is the last one. Okay, you see, the machine is getting much better than earlier in this same video, right? So you get the feeling. What happens in this case? This is basically a learning system used as an agent. The agent observes some environment and select among possible options the actions to be performed and get a reward that is positive or negative. So actually it's either a reward or a penalty in return to the action taken. So the learning step is basically the one that defines the best policy to get the most reward over time. Okay, so this is used a lot, of course, in robotics, but also in DeepMind's AlphaGo program that has beaten the South Korean champion in the game of Go in May of a few years ago. Okay, so reinforcement learning can be applied in many areas, robotics, drone control, and things like this, but also to market analysis, and also from traffic management and other social applications. There are interesting applications of this kind of technique. Okay, so this is the first basically classification. So let's try to move to the second different kind of classification, which is batch and which is online learning. So in this case, I'm classifying whether or not the system can learn incrementally from the stream of incoming data that I'm feeding to the system itself. So in batch learning, it doesn't learn incrementally. So you train on all the available data that you have. So basically you do it offline, and then you put the system online when you are ready. You get more data, no trouble. You stop everything, you put everything offline, you retrain, and you re-put everything online, and you redo your predictions and so on. So definitely this is quite resource hungry, and it has pros and cons. The advantages is that, of course, you can tune the model before you put it in production, but at the same time, of course, it's you need to stop potentially the system for a while, or let it run on a model that basically is not the most updated for a while, and things like this. Definitely, if you have a big amount of data, it requires quite some money, so it's resource expensive, okay? And it's not so obvious that in most conditions, this is exactly what you want to do. For example, suppose that you are doing machine learning on a rover on Mars. Potentially, you cannot stop everything, retrain, and let it go. Probably you need a system that is basically able to capture the images and do something in real time. You cannot really stop it, okay? Online learning is a different beast in the sense that you train the system indeed incrementally. If you think of what we saw before up there in this picture here, the data that is being fed is not fed only once. It's fed once at the beginning, and once the solution gets into production, you continue to run and learn with new data that come on the fly. Okay, this is really nice because every learning step is fast and cheap actually, and the system can learn from new data as the new data arrives. It's good if you have data that comes as a continuous flow, and it's good also if you have limited computing resources, like the data don't fit well in memory in the other in your scenario, and probably this is the only way to do it. Okay, so this is an approach that makes a lot of sense in many cases. So batch versus online learning. The third thing is the instance-based learning versus the model-based learning. So in this case, I'm classifying algorithm based on how they generalize. So generalization is very important as a concept in machine learning. It tends to, if you read around, it's very common that you find that machine learning seems to be described as an optimization problem, mostly because you have some cost function that needs to be reduced in the hope to find the global minima of that function in multidimensional spaces. It's certainly true because this is the way you do things. Gradient descent as an algorithm does exactly that, and it's used worldwide and fine. But it's not really important to get to the optimal minima in a sense. At least it's not important alone. The most important thing is that what you build, the model that you build, is able to generalize to data that were not used during the training. Okay, and this is basically a problem of the overfitting that we will be discussing. So it's very important in applying machine learning to make sure that you build a model that can be generalized. And it's a sort of a success, the key to success of any machine learning system. To make sure that you can approach well to generalization, you can learn on the instances or learn by model. Okay, the instant-based learning is very trivial, and basically you learn by similarity. Okay, so if you have a couple of options, you classify an instance as first case and not the seconds if that instance is similar to the other one that you saw in the training sample that had that specific label. So this requires basically a measure of similarity between instances, but once you build that, instant-based is really effective. Okay, so there is some learns and then generalizes to new cases by just comparing them to the examples that it has learned already or a subset of these. For example, in this case, in the picture, the new instance that you have with the cross will be classified as a triangle because if you look around, the most similar, so the most close by in the feature space are the ones that are basically green triangles. Okay, so the training instances belong to that class, so potentially you can say that the new one is of that type. Okay, quite the opposite with respect to instant-based is the model-based learning. What you do mostly in this case is you build a model by the training example, so thanks to the training example, and use this model to make new predictions. This is a completely different way to generalize from a set of examples. There is no distance measure, but actually just reliance on a single model that you build, which is your hypothesis, as it's called in jargon. So you reason on your data, you formulate an hypothesis on how actually each data feature contributes to the label, and you apply that model to the prediction. In the example before, the new instance, the cross, is being tagged as a green triangle, not because it's closer to green triangles, so it's not instant-based, but because the model says that there is a decision boundary, which is in the dashed line in the figure, that tells that that instance falls on one side of the feature space and not the other. Okay, so there is a model that exists that tells you the triangles to populate that portion of the feature space. So if you belong to that portion, you should be that kind of object. Otherwise, you are the different kind of object. Okay. So this is basically it in terms of classification. Now I would like to spend some minutes with you by discussing which are the major challenges, the pitfalls in machine learning, which are the key things you should be paying attention if you want to build a machine learning model that works. And there are a lot of simplifications, but I hope I touched most of the major challenges in machine learning in all possible projects. So let's see if the effort is successful or not for your taste. Okay, some of these challenges and how to attack and beat them are also discussed a bit further in the next lectures, both slides and code. So you will re-see some of these things. Some of these things, but it's probably the right time to introduce these to you because these are indeed potential pitfall and you need to be careful about all of these. Okay, so the main challenges in machine learning, as per my classification, can be related to bad data, bad algorithms, and technicalities related to the training. It's a major simplification of things, I admit it, but actually it's helpful in the discourse that we are keeping today. So let's start with the bad data first. A problem you might have is that you don't have enough training data. Imagine that you have your system similar to a baby that learns to spot vehicles by a dad or a mommy that tells this is a car, this is a bus, this is a motorbike, this is a car again, this is another bus, this is a car, but this is a taxi, or things like this. So how can you let the baby learn? You need to do this exercise a lot of days with a lot of patience, but you need traffic. You need a lot of cars, different cars, a lot of buses, different buses, etc. So in a way, machine learning is like the baby learning the vehicles, but it's way more stupid than your baby, because it can do these kind of things in seconds, and maybe the baby can take months to learn to do this kind of stuff, but actually the baby learns plenty of other things, okay? But the machine can learn this thing very well, provided that you give a lot of cars, a lot of buses, a lot of motorbikes. Otherwise, it fails. So you need to provide plenty of examples to learn. Otherwise, there is no way to make the machine learning learn anything from this case, which is a supervised machine learning model that you are trying to build for your machine. So this indeed needs large volumes of data, the volume V of the big data definition. This is a need. So a problem you might have in machine learning is that the training data that you have are not sufficient for your model to perform good enough. This is a problem. Another problem related to big data is the no representativeness of the data, which has nothing to do with the quality of the data, which I will be discussing in the next slides. By representativeness, I'm referring to the fact that the data you might be given can be a lot, can be huge. So for the volume, you have no problem, but they are not representative of the things that you are trying to model in machine learning. For example, if you are interested in modeling the kind of musics from the rock bands that you find online, for whom you can find videos online, if you use YouTube and their ranking, well, of course, YouTube ranking doesn't rank rock bands by ability to play the electric guitar. They rank a rock band by their popularity. And of course, there is a strong bias. And so you may end up in, if you select the 10 most clicked rock band on YouTube, you don't get those who play the best rock music. Potentially, you select just those that are more popular. And so the data set that you might be running the training on is not representative of your problem. So the model you will end up building is useless for your needs. Okay, so it's very important that you use a training set and you check that this is true, that is representative of the problem that you want machine learning to describe for you, and also should be representative of the problem you would like to generalize to. Okay, so if you do this mistake with YouTube, just to be clear, you built up a model that is able to identify the typical characteristics of a very popular rock band. So if you pass it a very good rock music, but it's not popular because it's your own band, for example, but you are very good at playing rock music with a guitar, and potentially this model will tell you that that's not even rock. Okay, because you are not popular for you to be, maybe you are not similar to those examples on which the training was done. This is a critical thing. It's called the sampling bias and need to be cured carefully in your modeling. So this is another problem with bad data. This, as I said, has nothing to do with the quality of the data, which is in this next slide. So the quality of the data is very important, and you might be suffering a lot from poor quality data. Okay, so machine learning systems, in a sense, are often referred to as garbage in and garbage out systems, in a way that they are as good as the data, the training data that you put in. If you put in training data that is full of errors, you have plenty of outliers, there is noise. For example, these data are taken from some measurements and they are poor quality with a lot of noise in that, in those, and things like this. The system, it will find it very hard to detect any patterns, any underlying pattern. So most probably the performance it will be able to achieve will be at least suboptimal, if not really completely garbage. Okay, so it is definitely not time wasted if you spend the time to clean up your training data, to make sure that you know your training data well and you cleaned them as much as you could. Okay, all the best data science team worldwide spend a significant portion of their time on machine learning problem. If you ask some machine learning practitioners, they tell you that potentially they spend roughly 90% of their modeling time in curing the data. Okay, so not 30%, 90%. Okay, just to give you a feeling. Another aspect of the bad data stuff is irrelevant features, or at least the importance of the features. this is still a garbage in, garbage out kind of comment, but the focus is not on the features, but more on the learning process itself. So the ability of a project to be successful largely depend also on you feeding the training process, not only with good quality data, but also with data that highlights the features that are enabling your model to learn. So actually you should help in all ways a machine learning system to help you, but you should help it in the first place, otherwise it doesn't help you back, okay? The feature engineering in general is the word that is being used, especially in non-neural network-based machine learning model, to describe the fact that you need to cure your features a lot. And this might include feature selection. So among the possible features that you have, select those that are most interesting to reveal some patterns in the data and exclude the others, like the correlated ones, the unnecessary ones, and so on. The so-called feature extraction. So the idea of building new features by existing features, by putting in place an unreal fake feature, but actually more expressive of some problem characteristics, okay? You can also use dimensionality reduction algorithm in that case. So some unsupervised algorithm might help you here. Or indeed, you can gather new data and add new features to your data sets. If that increases the expressiveness of your data set, your training have larger chances to be successful. This has nothing to do with the training technicalities yet. Okay, you can make the training be better with the same data set. But if you change the data set, the training in return will help you a lot. Okay. Okay, so let's move then to bad algorithms. So not talking about bad data anymore, but talking about bad algorithms now. Overfitting is a curse, okay? You might have a model that performs very well on the training data, but doesn't generalize too well on data that were not seen before, okay? The thing is very critical, and also you can point to the plots below to see what might happen as an overfitting in case of a regression. These lines would describe the data points, unless you really would like to go for the blue line that goes across all the data points. That's perfect as a fit. Probably a high order polynomial may do that, but who cares? You are not able to generalize to new data points, right? And at the same level, a classification in each feature dimensional space shown here by a line, that is the black curve. And actually, if the black curve is meaningful, but probably the green curve to distinguish the two, which is perfect, again, is not able to generalize much, okay? So the more complex you make a model, the more the model will be able to detect and describe the very subtle patterns in your training data set. But be careful, if the training set, and most probably it is noisy, or if you don't have many examples, so you are under the sampling noise that I told you before, then the model will likely be able to detect pattern in the noise. And so you find a model that is able to do things that you don't need, because you need basically to distinguish the characteristics that are useful in the data from the noise, not to model the noise. And if you have a model that is overfitted and models the noise, is not able to generalize well, okay? You can cure it by reducing the number of attributes, by applying techniques that is called regularization. In some cases, if that doesn't cure the problems alone, you can collect more training data and things like this. But you need to be definitely careful about overfitting. Also, underfitting is a problem, by the way. It's the opposite of overfitting. And it happens when your model is simply too simple. It cannot basically learn the underlying structure of your training data, which is more complicated than that. You can select a more powerful model. You can do some feature engineering. You can reduce the constraints of the models, or reducing regularization, for example. But it's a difficult game. It's always a trade-off across underfitting and overfitting, high bias and high variance, as it's used to say in jargon. And you need to find the just right solution that is basically in the middle. Don't be too simple, or you don't describe the data set. Don't be too complicated, overfitting the model, the data points, because otherwise you are perfect on that data set, but you cannot generalize, which is your ultimate goal. Training technicalities, still on the main challenges of machine learning. Then you need to be careful, as you understood, to do something on your data in the best possible way. And since you need to take care about the generalization, the only way to know how well your model will generalize to new cases is to actually try it yourself on your data. In many cases, you don't have the new data. You will be needing, for example, to wait for new data to come, okay? So the best idea to do, and it's done by all practitioners, is to split your data in different sets, at least two in this context. Then we'll see it's more complicated. You can split the data set into a training set and a test set. The idea is that you train your model using the training set and you test it against the test set. The error that you get on new cases, you call it generalization error. And this is what you are expecting to get in real cases. So there is no bias in your model if you try how it works on data that were not used in the training. That's why you split the two things, okay? If you have a very high generalization error, probably you are overfitting, and so you need to cure the overfitting and things like this. There are, of course, more refined options that exist. Another option, for example, is what you ask yourself if you are hesitating between two machine learning models. What should I use among these? And probably you train both and you compare how well they generalize on the test set. Okay, maybe this helps you to pick one. But actually, how do you regularize, for example? Okay, there is an example here that tells you that what happens if I regularize at a certain extent and I see that I'm curing overfitting, but still I have a 50% of error with new unseen data. What should I do? Okay, so a solution, the typical solution that is done is to have another set, the so-called validation set that should hold out from the total data set that you've been given. The idea is that you train multiple models with various hyperparameters on the reduced training set, okay, which is the training set minus the validation, and you select the different models based on which is the one that performs best on the validation set. Okay, once this all down validation process is done, you retrain the best model on the full training set, re-putting the validation set inside, and this gives you the final model. Once you are ready, then you check the final model on the test set to get an estimate of the generalization error. So at the end, you've been given a data set, you need to divide it into three pieces. This is the typical statistical division of your training of your data set into three pieces. Training set, the one on which I train, validation set, the one on which I validate, and test set, the one on which I check my final generalization error, okay? This, of course, might be doable or not, depends on how much statistic you have. Suppose that you use 70% of your data for training, 20% for validation, and 10% for test. This means that your model will be trained on only 7 examples out of 10 in your data set. Well, it depends. If you have 300 of examples, it's tricky, right? So you would like to have more examples. Can you have them? Well, maybe you can't. And so what do you do? If you have billion of examples, you can afford it. But in general, there are other techniques to make sure that statistically wise, you are doing the best thing. And one of the options to go for is the so-called cross-validation, okay? So the idea of the cross-validation is quite amazing if you think of it, because it does validation repeatedly using many small validation sets. So basically you divide in pieces your training set, you take one out, you make the model, you validate against this as a validation set, and then you have a number. You put it back, you take the second out, you train, you validate with the second, and you put it back. You take the third out, and you do like this for all the possible so-called folds, okay? Once you do this, basically you have many trainings done in a very clever way. Actually, this gives you some accuracy, some performance numbers, but also a standard deviation if you want, because you have repeated things. So you pay the price of training more times, but you are much better and less static than before, okay? You are less open to problems like you don't have very well stratified subsamples, so statistically you are more solid. It's a very nice technique. We will also in the end on some cross-validation, okay? And that's basically it for this part in which I tell you the generic information, let's say, about machine learning. So I would like to move now 1 second on a very pragmatic section that tells you something about the Python libraries that we might be using today and the tools that we might be using today, and also the frameworks that are used in machine learning in general, okay? Good. So one option for you, if you are a very beginner, is definitely to install and use Jupyter for prototyping your machine learning projects. Jupyter is very simple. It has a very neat interface, can be used as an open source web application that makes you create and share whatever you want, code, plots, documents, etc. So you can write code in it, you can write text, you can write in LaTeX, you can embed videos, you can do whatever you want. It's very good for streamlining an entire workflow and excellent, I think, in the prototyping phase. This is something that comes with a lot of Python distribution, or you install it yourself. If you use, for example, Anaconda, you get it for free, and it's very easy to launch. And there is a link up there, so go there and check to get more familiar. Today, we will not use Jupyter's because we don't want to go into any Python or installation party whatsoever. We don't have the time. So my idea is instead to use basically Jupyter notebooks on the cloud. An option is using Google Colab. Google Colab, and you can learn more by going there and check yourself, is indeed, if you allow me this oversimplification and more than that, but it's like running these notebooks on the cloud. And there are really neat set of interfaces, a lot of also shortcuts that you could be using. If you know Jupyter ones, you can easily learn the Colab ones, but it's also easy and also to go around and click yourself. So should not be complicated. The very interesting thing by Google Colab is basically the fact that you can change somebody else's code and interface everything with your Google Drive. So a proper way to get started, remember you are on the cloud, is that you create a new Python notebook, or you open an existing notebook that I will be giving you from Google Drive or GitHub, or you upload it from your laptop, whatever. Once you have that, you save a copy on your own Google Drive and you code on that one. That one gets saved. Don't do the mistakes to skip this step, because Colab is not available for you in terms of notebooks forever. The idea of Colab indeed, is that it's being given for you, and some resources for free, but also with some constraints. Let's see what they give you first, and let's see the constraints later. Once you open a Colab notebook, as we will do it, you get something that is called a Colab runtime, which is basically a Google virtual machine that is dedicated to you for a while. At the beginning, what you get is that you are a runtime based on a CPU, and you see it in the top right corner in the interface. You will see it. Once you get there and you click on connect, the states of the virtual machine go through connecting, allocating, initializing, and at the end, when you are done, you see a widget that monitors the RAM and disk utilization. In this case, you are on a CPU provided to you by Google Cloud Platform, and you have this RAM and this disk available on that machine. Then, if you want, and we will do it, you can go to the runtime and actually change the runtime type. And under this option, you will see that you can even select to have a GPU. And if you do so, on the top right corner, you will see that Google Cloud Platform is giving you, indeed, a GPU to run your Python notebook. So you don't need to buy anything, you don't need to install anything, you don't need to ask anybody to access the GPU for your attempts. You can have a decent size GPU for some, let's say, beginner level kind of hands-on and exercising on Google Colab without doing much. And actually, you can also access the tensor processing unit, but let's not go to that at this stage. So what happens behind is indeed that there are different environments that are available to you as runtime. So the interface is the same, but behind you might be given very different beasts, but not forever, of course. So in the FAQ page of Colab, it said that Colab is intended for interactive use, and they don't support long-running background computation, especially on GPUs, so they will be stopping this. Of course, they don't want to give this to you for free, and then you spend all of it using cryptocurrency mining, right? So they do the following. The web interface, if you do nothing, disconnects your runtime after 30 minutes of unattended connection. So you need really to go there and push a button to have another 30 minutes. But if you do not go nothing, you lose basically the connection to your runtime. And even if you continue to do things, you get the shutdown of that specific runtime after 12 hours, okay? This is to prevent long-running computations. But it still needs, because it's something that you get for free, and the GPU, we will see, are very useful for our workflows. And by the way, which GPUs do you get? There are tricks, you can get others, but the vanilla way to use Colab is to get a Tesla K8. If you do so, and if you see GPU in the top right corner of the interface, it means that most probably you will see a RAM that in global can be at 12 gigabytes, and a disk roughly is of the order of 50 gigs, I would say, and the GPU that you have is a Tesla K80. Is not amazing, but it's not awful, and definitely it speeds up linear algebra with respect to using just a CPU. So you will see the difference also in the end zone. Okay, good. Other things you need to know, you may or may not know, and given from the feedback that you will give me today, I will also be more than available to give you some notebooks that allows you with some exercises to get practice among these about these libraries. The one thing that probably you need to work use quite often if you prototype machine learning models in Python is NumPy as a library. NumPy is a third-party package that is around, of course, the Python language as many others, and supports scientific computing. The most important things to know about that is that it provides you multi-dimensional arrays. And these are used so much to manipulate the matrices, do all possible linear algebra, diagonalization, inversion, transpositions, whatever you need to do, NumPy can support it nicely. So a good way, if you are a real beginner, to spend your time is to get a good course on NumPy. NumPy basically has also published on Nature. So this is sort of an enabling technology, let's say, for science, which is quite important in our community. Pandas is another thing probably you cannot live without. Pandas is an open source library that gives you data structures and data analysis tools. We will use a lot some of the data structures in Pandas. Today, mostly data frames, but there are other things. There are series, data frames, indexes. It's a very nice way to deal with your data sets, especially if you do it for visualization and for data analysis. It's high performance, it's very easy to use, and it's something you cannot probably live without. You need to plot something. The minimal to start with and the minimal you need to know to get easy through the code today is something like matplotlib. There are so many other things. Choose the one you like the most, like Seaborn or other stuff, but you need a package that allows you to make plots and visualize your data. My choice 0 is definitely matplotlib. Then, of course, you need something to do machine learning itself, apart from the surroundings, okay? And there is a lot, okay? So it's tricky because today probably the tools is defining what you do quite as much as they define how you do things. So you might be doing things in a way and to a goal because you're using a tool that makes that easy and not another tool. So it has pros and cons, of course. But one thing that probably you need to get in your data science backpack, if you are interested in a journey through machine learning for any application like industry or science, you should get familiar with at least that there might be other choices, but most commonly would be Scikit-Learn, Keras, and TensorFlow. Keras is a high-level thing. TensorFlow as a most probably the best backend you can have behind, or eventually know something about PyTorch in alternative or together with TensorFlow and Keras, and potentially other libraries nowadays like FastAI, H2O, AI, etc., other stuff like this. Today, and for the entire duration of the day, I will not be using anything that is aside from Scikit-Learn, Keras, and TensorFlow. What's Scikit-Learn? Scikit-Learn is an amazing set of tools for machine learning. Okay, you have tools in data mining in general, in data analysis. It's built basically on NumPy and matplotlib for scientific computations and plotting respectively. And we will use Scikit-Learn in our labs today. TensorFlow and Keras definitely is the answer to your question, should I adopt some tool, some framework that has a modern description, a good implementation and application of learning algorithms, and also covers neural networks, with Scikit-Learn actually has this as a sort of limitation in a way. Keras definitely is a high-level wrapper for backend libraries, which may not be TensorFlow, but in this case would be TensorFlow. Okay, you can use it with Caffe, with other stuff behind. TensorFlow is low-level implementation. It's really relatively effective. It's really effective because it allows you to run in multi-threaded CPU environments, in multi-GPU environments, and basically, if you do things properly, this is all transparent to you. So you work in Keras, and behind you have a backend that does the bad stuff for you. This is for an applied machine learner, probably the best thing to work. Okay. Why these? Because they are popular, they are widely adopted. There is a large community supporting this. If you have questions, this is open source. You can find a lot of support, training, tutorial, material, examples, etc. Everything started roughly in 2015 when TensorFlow became public from Google. And definitely, I should note that recently PyTorch is also catching up a lot. And for many scientific endeavors, PyTorch is considered the same as TensorFlow, if not better, but they are very different history. I don't want to go with a sort of dogmatic kind of discussion among the two. I think you should learn what fits better for your taste and for your needs. This stuff that we do today focuses on Keras and TensorFlow, but that doesn't mean you should not learn PyTorch and other stuff. It's quite the opposite. Probably you should be familiar also with those. Okay. So TensorFlow, as I said, came out from Google in 2015. It's a software library that basically does numerical computation based on data flow graphs with nodes in the graph to represent all the mathematical operations, and basically computations that flow through these. This is the reason it's called TensorFlow, because basically all the multidimensional data arrays in jargon are called tensors, not in the very well defined definitions, mathematical definition of tensors, but you can call them as just tensors if they are multidimensional arrays. This basically flow through the graphs. Okay. So in principle, TensorFlow is not for neural networks, but it's so perfect as a match to implement neural network that definitely most of the people nowadays use it for that. Keras, as I said, is a layer on top. So it's a wrapper you can interact with in Python that has behind a lot of other things. You can have it with Theano, CNTK, etc. We use it with TensorFlow as a backend. The pros is that most of the low-level operations that you don't need to take care of in principle, unless you really need, so can be sort of forgotten. So let's outsource that stuff to the underlying backend layer, and you do the simple thing like add me this layer to the network, add me this other layer to the network, configure it like this, do the training. So very high level stuff. And below, of course, TensorFlow in this case does whatever needs to be done. The cons of this approach, of course, are clear. You can sacrifice because of the better user interface, some flexibility and some functionality. But if you need to go deeper, just forget about Keras and do everything straight on TensorFlow. It's a bit more complicated, but you can do that. Okay. So the idea of Keras that has behind the entire project, the Cholet basically concept of things, which is should have a lot of appreciation by the community indeed, is that you should be able to go from your idea to a result with not a major delay. Then, of course, if you need to do something more, you go deeper. Okay, the labs will use Keras. We will not see TensorFlow code directly, but we will see some Keras code that use TensorFlow as the backend. Okay. Is this okay? I think this is the first hour of our long day. I'm roughly 2 minutes behind, so it's sort of acceptable, I hope. This is okay. This is everything I wanted to show you as a first introduction to the topics that covers a lot of things, as you saw. So now it's time that we change gear a bit. We go into our first lab. Our first lab is called regression. So we will start to attack a specific machine learning problem of a regression. And this is where basically we could do things together if you want. Okay, so now let me just do one thing. Let me take from my notes the links to the Google Drive where you can find all the notebooks that you might need. Need access to the chat. Okay, let me see. So everyone in the meeting should be getting from me a link on a GitHub for a Google Drive. And in a second, you get also a link to a GitHub repository. Here it is. So I hope you can see it. And these are basically the same. So you don't need to use both. It depends on how you are mostly familiar to one. You might prefer to use one. So on Google Drive and on GitHub, you don't find the slides. You find in both the same version of the Python notebook that we will be using. Okay. Now I'll show you myself on my screen. Let me just go to the repo. Okay, let me stop sharing this one, and then now maybe I share my entire screen so you see exactly what I'm doing. Let me know in case you don't see it, and in case especially the links are not big enough. Now I'll try to put everything with good font size so you can see it. So we need a few minutes to set up, and then we start with the lab, of course. So the laptop that I'm using to project is getting a bit slow, probably needs to be helped by another laptop that I have, which I will do after the break. But let's see if we can survive with that for the time being. Okay, let me see. You should be seeing this big enough, hopefully. And it's getting very, very slow. Let me see if I can do something from perhaps this other screen. Okay, let's try to do like this. 1 second. Huh? So I need to stop sharing from this one. And I start sharing from this other one. If it works. So hold on a second. I need to change the permission on this guy here. Okay. So let's see if this is quicker. Okay, so let me see if I can. See this one. Okay, so now you should be able to see this one much better than the one that I was using earlier. Okay, so let me know if you just pick up if you don't see the screen, or if I'm saying something and doesn't match what you are seeing, of course. So basically in this link that I gave you on the chat window, you should be able to access this repo here. Okay, well, there are 4 Python notebooks, Hi, P, I, and B, Y, and B. Okay, and basically the one we would like to start from is the first one, classification part 1. This is not the optimal name. I will change it later. I will change it later. No, sorry. The regression, this one, the lab regression one. So we need to use it on Google Drive, so on Google Colab. So one easy thing that you can do is right click on it, open with, and go to Google Colab. You can do the same, of course, if you click on it through some widget, but this should be as giving the same results as this one. So basically, this is how it looks like. Let me make it a bit larger too. Okay, I think you can read it from here. So basically, this is the notebook that I will be using behind the slides that I'm going through in a second. The slides will show some snippets of code with comments, and I will talk on this. We can switch, go from one side to the other from time to time, but actually you can have what you want under your eyes, and it's much easier to you perhaps to have the code than the slides. Somehow the slide you can see it from Zoom, right? So all these come with some description, not so much, but there is easy code that you can very easily, if you're familiar with Colab or Jupyter, you know how to do it, but you can very easily just launch without doing anything by just clicking with this little, on this little play button, so that something happens. So you are connecting, you see, on a virtual machine up there, connecting, initializing, connected. So you get the monitoring widget that I told you before. And once this is done, you get the thing executed. Okay, and this happens for all the cells that you have behind. The practice R2 stands for regression 2, regression 1, and things like this are there exactly to point you from the slides to the code. So to make sure that what I'm talking about in the slides have a connection with what happens on the code, I have this little hanger that should help you not to get lost. Okay, so this is basically it. Now I would like to reshare my desktop here and come back to the labs with another set of slides. Which is the one for the regression lab. So we start now for 20 minutes and then we go on a little half an hour break as per the program. During the break, by the way, I will be staying around, maybe taking a coffee quickly, but if you have questions on the chat window or just unmuting, if I'm here, of course, I hear you, but otherwise write in the chat window. I'm not 100% sure I will be able to do all the question and answers if you have a lot in real time, but I will keep the chat and come back to you. There is a mailing list on the participants, by the way, so I'm also able to reach you back with some answers if you have more detailed discussion needing and coming out from the time we spent together. Feel free to just speak up in a way or another, and I'll come back to you. Okay, so let's see this little lab on regression, how this look like. Okay. Is everything clear? Does anybody have troubles in getting into either Google Drive or GitHub to access on Google Colab the code to see the slides? Should I assume that everything is okay? Can I continue? If I hear nothing, I assume so, of course. Okay, good. So what about regression? So we need to attack a problem and sort of make it look like a real one somehow. So we make a simulation of a problem and we try to go through some steps of the problem. In this case, a regression case, then we will do something for a classification case. The idea is that you need to frame your problem, try to understand it, select a way to measure your performance as a starter, very important to do it at the beginning, get the data you need, explore the data you have with some descriptive statistics, pre-process the data, so prepare the data for machine learning, select the model you want to use, train the model, fine-tune the model, pick up some way to present a solution out, and eventually, if this needs to go into production, you need to launch the model, monitor a model, and then maintain also the new system that you just deployed. The last part, of course, we will not cover it. We are not going to that level. But actually, the first steps are sort of a little pipeline of actions that you should probably be following for all your machine learning projects, not only this little lab that we do today. So today we start with a regression case. So the first lab is that we try to model the prices of house in California uses the California census data. So the idea is that for a while you should be pretending to be a data scientist that has been hired by a real estate company in the US. And specifically in California, your goal would be to predict the price of a house given a set of parameters of the house in California. So you have the California housing prices dataset that is available, by the way, and published with some little information that I'm telling you, but there would be also other information that have been changed to make this data set useful for starters to get somehow familiar with machine learning. So you have the population, you have the median income, you have the median housing price, you have a lot of details. And this is sort of grouped for every block of people, roughly 503,000 people that are called districts. Okay, so we have districts of people in California. For each district, you have in your table of data one line. For each line, you have a lot of attributes, and you might use these as feature in your model. You have many lines because you have many districts throughout the California region. Okay, so your model should basically use this data and learn from this data and be able to predict the median housing price in per any district, okay, given all the other information that you've been given. This is basically the task. And the data set somehow looks like this. So this is every small point that you have there, depending on the size, is basically a data point that you have. The color of it is the median house value, which is your basically label. So you have already the labels in color. This is a supervised machine learning problem, as you will see in a second. The idea is that if you are given a new district that is not there, you should be predict which is the value of the house in that district. Okay. So first point, you should ask yourself a lot of questions. You should think that in this phase, you should not think about machine learning. So building the model is not your goal. You should ask which are the goals. And you don't work in an isolated system, perhaps, as a data scientist. So you need to stand up and ask your questions. Example of good question to ask for this problem. What are you're going to use my model for eventually? Okay, this helps you a lot because you know then how to approach the problem, which are the algorithms that you should be selecting, which is the performance that should be achieved, and which should be enough if you need to do more, how much effort you need to invest in different parts of the work, etc. Second question you need to ask, what is the current status of study of this problem? If it's a new problem, fine, but for example, in science, you should be understanding which is the precision that other non-machine learning based method achieved and things like this. Okay, this gives you a reference performance, so you know if you are better than the reference performance. For example, this is typical in science. If you try a machine learning approach on a problem that has already been attacked by traditional approaches, you don't just try. You want to see first, is there a chance that machine learning will put me in a position to say that my model is better than before, better than the state of the art, right? So another aspect is, which is the full data pipeline in which my solution will live? This is very important and often neglected, okay? A data pipeline is a sequence of components that do data processing, and it's done very commonly in machine learning. And you are working probably in different teams, etc. You need to make sure when your model is going to be used, what approximations have been done earlier, what probably collapse into easier solution will be done afterwards. This is very important. Otherwise, you work for nothing. Probably you spend a lot of efforts for something that was not really needed. Okay. So then you should make some assumptions, which is the second step. So thinking about the problem, as I told you, you should already be able to say, is this supervised? Is this unsupervised? This is reinforcement learning kind of approach that I'm looking for. Is it classification or regression? Should I use batch learning or online learning? So you should think about it for a second. There are, of course, hints that I gave you that should tell you already what kind of problem you are living with at the moment. And definitely, this might point you to be a supervised learning task. You are given the median housing value in all the districts in the data set. So you have labeled training examples, which is very good. So you have the truth for this. So you can sort of architecture this as a machine learning, as a supervised machine learning problem. Second, you've been given the data already, right? Nobody told you that the data are going to change. These are data from the 90s, by the way. So other things, other consideration might apply. This data is not changing. And in all this data, you only need to predict one parameter. So it's a regression. The parameter is in dollars. So it's a real number. It's not a classification. It's a regression. You predict only one parameter. So it's univariate, not multivariate regression. Okay. And definitely the data are what they are. So you don't need online learning. The data are not amazing. They should fit in memory. There is no reason to think about something complicated. So this is, in a way, a supervised machine learning problem of univariate linear regression, univariate regression that can be attacked with batch learning, okay? If you have the feeling you did nothing so far, probably in real life, you should be thinking that you are starting from the middle here and you are around of yourself, plenty of different choices of possible algorithms and techniques, all with a lot of sub-choices possible of sub-algorithms and sub-techniques, okay? So it's really a zoo. So if you think you did nothing by just analyzing the problem, my message in this slide is that you already made a very, very precise decision. You studied the problem and you know already which is the direction. This is a supervised learning kind of problem. This is regression. Then there are options, of course, but it's not a zoo anymore. So you already sort of constrained your possible solution in a domain that actually it's more under control than the entire zoo, okay? So you know that he is supervised, you know it's univariate regression, and you know this is batch learning, okay? Now that you decided this, you should recheck if your assumptions are correct. So in the overall work pipeline that I told you before, is there anything that should stop me from continuing with supervised univariate regression batch learning? For example, suppose that your predictions are going eventually to be clustered into much coarser grain categories. So you do this as a regression problem to predict the price. But at the end, this was not needed because somebody else after you will just classify prices as cheap, medium, or expensive. Well, tell me earlier, because then I don't do this problem as a regression one. If getting the price perfectly right is not important at all, many of my efforts are unnecessary. And if you just need the three categories to be right, probably I reframe my task as a classification task, a multi-class classification, a multivariate kind of classification. But actually, it's much easier than predicting the price with some resolution. Okay, so this is why it's important. Make sure that you know exactly what things are going to happen after you did your work. Okay. Then we will use some notation. I don't want to be heavy on notations, but just to make sure that everything is clear to you. When I talk about M here and there, I refer to the number of instances or examples in the training set, so the number of districts in this case. When I talk about X's, it's a vector, and it's a vector of those attributes that I treat as features. So the population in a district, the total number of houses in a district, the total number of bedrooms in the houses in a district, these are features. Y is the output variable, the so-called label, it's my target, okay? There is one per example, which is the median house price that I know, the truth, okay? And then within parentheses, the XY is a single training example. If you think everything in a table, this is one row of the table. The features are the column plus one that is the label. All the rows are the training example, okay? So this is, for example, on the left-hand side, a way to draw a single feature vector, okay? And this is a single connected to that specific example in the training set, the single true value, the single label of that feature vector, okay? Good. So another thing that we need to do is select a performance measure. This is a regression problem, and the typical performance measure is the root mean square error, so the so-called RMSE. You can actually use also the mean absolute error, the MAE. All this comes from statistics, of course. You all know what that is, okay? You can decide what you want to do. The RMSE, usually being the roots of sum of squares, is the Euclidean norm, the so-called L2 norm. The MAE being the sum of the absolute is the so-called Manhattan norm or the so-called L1 norm. In general, it depends. So the higher the norm index, the more it focuses on large values and neglects small ones. So RMSE is more sensitive to outliers than the MAE. If you have outliers, probably MAE is better. Actually, if you are in a bell-shaped curve kind of distribution of the data, probably the RMSE performs well, and generally it's preferred. So in many cases, probably the RMSE is just fine. I would suggest we stick with that as a performance measure. You can check the two. The code actually check both, but RMSE could be my reference. So I would like to have a small RMSE, because RMSE, you see how it's built. Just as a reminder, you know that from statistics, statistics and machine learning, of course, use different jargon, but you know what that is. Behind we have all statistics. This is basically the square root of the squares of the differences among your hypothesis for the function that connects your inputs to the true value and that true value. So how wrong you are in your prediction for each of the examples, running as an average over all the examples you have in the training set. So it's a way to see how bad I was in doing the prediction, basically. Okay.